Good evening, all. In this episode of Sleepy Math, we are going to take a look at the 16-point unit circle for trigonometry. Now, the 16-point unit circle is a very useful tool, and basically what it comes down to is it is a circle with a center at the origin and a radius of 1. You can probably draw a better circle than I can. At least I certainly hope you can. And if you can't, that's okay. I'll draw a better one for the next circle that we're going to use. The idea is that any point on the circle can be connected to the center and form a radius, like you're seeing right here. And you can drop a perpendicular to the x-axis from wherever that point happens to be, creating a right triangle. The coordinates of the point then are going to be cosine of x for the x value. I should say cosine of theta, silly me. Theta is going to be our angle. So x is cosine of theta, and y is sine of theta. And this is also has something to do with polar coordinates. Anywho, so we have cosine of theta is our x value, sine of theta is our y value, and the reason is if I kind of break this triangle out, take it outside of the circle, we have the hypotenuse, which is 1. The reason it's 1 is that this is the unit circle. There's 1 unit for a radius. And if this is theta here, then I have an adjacent side, and, oops, I wrote hypotenuse. I didn't mean to. I meant to write O for opposite. So we have an adjacent side and an opposite side. Well, sine of theta is equal to the opposite over the hypotenuse. So sine of theta would be O, which, if we go back to where our actual triangle is, that's how far above or below the x-axis it is. That's my y value. Likewise, cosine of theta is adjacent over the hypotenuse, or just A, because it's over 1, and that's going to correspond with the x value, how far left or right of the y-axis does the point lie. Now, for the 16-point unit circle, the idea is there are 16, I'll call them critical points, that one could know in a unit circle. These are the ones that are worth committing to memory, if you will. Mostly we are going to work in the first quadrant. That's the upper right. The second quadrant is our upper left. The third quadrant is our lower left. And our fourth quadrant is our lower right. The thing is, in the first quadrant, everything's positive. So that's where we want to do all of our work. Any angle that ends up in one of the other quadrants, we will use our first quadrant as a reference. I'll explain that later. So let's start. We have 0, we have 90 degrees, which I'm going to call pi over 2, because I think radians are cooler than degrees. And then we have pi. We have down here, I don't have a ton of space, I can zoom out a little bit though. There we go. Down here we have 3 pi over 2, which is the same as 270 degrees. And then when we get back to 0, that's also the same as 2 pi. I'm not going to write that in. In the first quadrant, in addition to the quadrant angles that we have of 0 and pi over 2, I want to draw 3 more. 1 corresponds with 45 degrees, 1 corresponds with 30 degrees, 1 corresponds with 60 degrees. I'm not using a compass, so these probably aren't exactly correct, and that's okay. In radians, what we have here is pi over 6, pi over 4, and pi over 3. So those are the 5 angles, really, that we want to work with, and everything else will be some sort of reference. We have 0, pi over 6, pi over 4, pi over 3, and pi over 2. Before I go to what the values are, because I'm going to have to draw these on a separate angle, I just want to illustrate how I would actually work with some other angle. So let's say hypothetically I had an angle that was, let's call it 5 pi over 6. That's going to be here. So 5 pi over 6. What I would do is I would note that the angle from here to here is the same as the angle from here to here, except reversed. The angle between 0 and pi over 6 is the same as the angle between pi and 5 pi over 6. The difference in radians is pi over 6. So whatever my x and y are at pi over 6, I'm going to use the same things over here in my second quadrant. You'll notice the y value is the same. How far above the x-axis am I? The x value, however, is going to be the negative. It's a mirror image, so negative x. And that's why we use reference angles, because it's very easy to just change the things between positive and negative depending on whether x is positive or is negative. So we can always reference our first quadrant reference angles. Okay, let us make another circle. And this time, instead of putting the angles down, I'm just going to put what the x and y coordinates are. So our quadrant angles, those are pretty easy. 0 corresponds with 1 comma 0, x value of 1, y is 0. Likewise, if I go to pi, it's going to be negative 1, 0. Let's make that look more like a comma. For my pi over 2 and my 3 pi over 2, I'm going to have 0, 1, and 0, negative 1. Those are my 4 quadrant angles. Now, the next 3, if you already have them memorized, awesome. This is just a refresher for you. If not, you may find that I am going to have a little trick for you that's going to help you remember them. Right now, I'm just going to tell you what they are, and then later we'll make a chart for how to remember these things. So, this corresponds with pi over 6. This is 30 degrees. Cosine of 30 degrees, or pi over 6, is radical 3 over 2. And sine is 1/2. Zoom in a little more so I can draw this a little easier. I'm actually going to jump up to 60 degrees now, because what's great about 60 is we just reverse the two. Sine and cosine basically switch places. So cosine of 60 degrees, or cosine of pi over 3, is 1/2. And the sine of that angle becomes radical 3 over 2. And then we just have this one that's my pi over 4 or 45 degree angle. And for those, x and y are equal to each other, which I would say is of interest. And in both cases, it's radical 2 over 2. I can make a better 2 than that, and therefore I will. Much better. Now, if you're curious, go ahead and apply the Pythagorean theorem on all of these. If you square the x values and you square the y values of any one of these points, add them together, you will get 1, the square root of which is 1. And hopefully that makes sense, because every single point that we put on this unit circle can ultimately be turned into a right triangle, and the Pythagorean theorem should hold true for all right triangles. Okay, so that's really what you need out of a 16-point unit circle, even though I did not put in the other, 9 points. You can also do these on your own if you want. It's all the same values, just some of them are negative. And I'll leave that to you to figure out. So that's 16 points all the way to the unit circle. Those are the ones that you really should either have memorized or be able to easily reference. Now, when it comes to memorization, how do we remember what's what? Well, it's actually pretty easy, at least for sine and cosine. Tangent may be a tiny bit trickier, but if you remember that tangent is the sine divided by the cosine, then that actually becomes pretty easy as well. So what I'm going to do is I'm going to make a chart, and the chart is going to have the angle, the sine of that angle, and the cosine of that angle. We're only going to go from 0 to pi over 2. So we're going to go 0, pi over 6, pi over 4, pi over 3, and pi over 2. I'm not going to draw the lines in between them. If you want, you can write the degrees next to yours on your chart, or if you're just following along and trying to fall asleep, hopefully you're not writing anything and you're just watching what I'm doing. So, sine of 0 is 0. Cosine of 0 is 1. Sine of pi over 6 is 1/2. Cosine of pi over 6 is radical 3 over 2. Sine and cosine for pi over 4 is radical 2 over 2. Sine of pi over 3 is radical 3 over 2, and cosine is 1 over 2. And finally, sine of pi over 2 is 1, and cosine of pi over 2 is 0. Now, I think it's pretty obvious that sine and cosine are the same pattern, just in the opposite direction. We go 1, radical 3 over 2, radical 2 over 2, 1 over 2, and 0. So cosine is consistently decreasing between 0 and pi over 2. And sine goes from 0, 1/2, radical 2 over 2, radical 3 over 2, and 1. So sine is increasing from 0 to pi over 2. Now, how do you ultimately remember that? Well, I'm only going to show you this once, and just know that it applies both forwards and backwards. What I'm going to do is I'm just going to write a bunch of things over 2. Let's give myself a little more room here. Tiny bit more still. Okay, and now I'm going to write 0, 1, 2, 3, and 4. Because if I just do everything over 2, that's a pattern. 0, 1, 2, 3, 4, that's a pattern. And now what I'm going to do is I'm going to put a square root over the numerator of every single one of these. And then I'm going to note what they're equal to. Because the square root of 0 is 0, so 0 over 2 is 0. The square root of 1 is 1, over 2 becomes 1/2. Square root of 2 is irreducible, so we'll keep that as square root of 2 over 2. The square root of 3 is irreducible, that's the square root of 3 over 2. And the square root of 4 is 2, 2 over 2 is 1. And would you look at that? 0, 1/2, radical 2 over 2, radical 3 over 2, and 1. That exactly matches what we put in for sine. Cosine is just the reverse. Well, that's it for today. I hope you enjoyed. I hope you're asleep. And if you're not asleep, I hope that you'll subscribe and perhaps tell your friends about this. Have a great night.